In this video, we are going to talk about Gaussian elimination method and its close relation to the matrices and row operations. Let's consider an example of a system with three linear equations and three unknowns x, y, and z. The basic idea is very simple. That is, we are going to use the first equation to somehow clean off the x's in the later equations, and then repeat the process for the y unknown. Before we do that, let me go ahead and switch equation 1 and equation 3. This is for simplicity purpose. As you can notice, there is only one x on equation 3, so that will help us simplify our computations later on. Now that we have the single x on the top, and we are going to use it to eliminate the 3x and the 2x below. In order to do so, we first multiply the whole equation 1 with negative 3 and add that directly to equation 2. If we do that correctly, we should be able to get negative 5y plus z equals negative 3. And we are going to mark and note by writing that equation 2 an arrow, which means it has become equation 2 itself plus negative 3 times equation 1. Similarly, we are going to multiply equation 1 with negative 2 and add that to equation 3. And as a result, we are going to have negative 2y plus z equals 0. Now we have successfully eliminated all the x's below the first equation. The next step is to repeat the whole process for the unknown y on a smaller scale. Because neither 5 nor 2 is a multiple of the other, to help us simplify our later computations, we first multiply the whole equation 3 by negative 5. If we do that correctly, we should be able to get 10y minus 5z equals to 0 as below. Next, we'll try to eliminate the y below. In order to do so, we multiply equation 2 by 2 and add that directly to equation 3. We should be able to get negative 3z equals negative 6. Now we are going to find the solution for the system of linear equations by tracing back from below. Starting from the easiest equation from below, negative 3z equals negative 6, we can easily find z equals 2. After we know z equals 2, we are going to replace that back to equation 2 and we are going to find y. After we know both y and z, we are going to replace them back to equation 1 and we are going to find x. So the solution for the system of linear equation is the column vector negative 3, 1, and 2. And because we are tracing back from below, this is called the backward solution. Let's look at what we have done so far. We have used Gaussian elimination method to successfully solve the system of linear equations. But do you notice that there was something that we had to write over time again and again? For example, the x's, the y's, the z's, the plus sign, the equal signs, and the curly brackets. To save us time, why don't we just erase them all and keep in mind that they are there in case we need to trace back. For example, the first column is always associated with the x variable. The second column is associated with the y variable. The third column is associated with the z variable. And the last column is reserved for the coefficients on the right-hand side. Before we do that, let me go ahead and put the number 1s in front of the single axis, y's, and z. The purpose is to prevent us from misthinking that there is nothing there after we erase them all. Also, where we don't see any x or y are where we have 0x and 0y. Now we are ready to erase all the unnecessary things. And what we end up having is something look like matrices. The first matrix is actually called the augmented coefficients matrix for the linear system. In addition, we draw a line to help us remember that there is a major difference between the coefficients in the last column and the others. Also, what we did on the equations turned out to be what we would do on the rows. And these are called the row operations. If you pay attention, you would see that the last matrix is actually the staircase matrix. In other words, it is in echelon form. Once you have the echelon form, you can start using the back solution method to get x, y, and z. For example, we'll start with the last row, which is -3 and -6. -3 is on the third column and it is associated with the z variable. So we in fact have -3 times z equals to -6. That leads to z equals to 2, and from there we can easily get y and x. However, if we try to reduce the echelon form to the row reduced echelon form, then you will see some magic. In order to obtain the row reduced echelon form, we first need to turn the pivot entries -5 and -3 into 1, and also turn all the entries above them into zeros. In order to do so, first we divide row 3 by -3 as an attempt to make 1. And now we use the number 1 to zero out the other entries above it. To do so, we subtract row 2 by row 3 and subtract row 1 by row 3 as well. Next, we divide row 2 by -5 to make 1. Again, we use the number 1 to zero out the entries above it. In this case, we subtract row 1 by 2 times row 2. And congratulations, you have obtained the row reduced echelon form for the augmented matrix of the original linear system. Do you notice that the column on the right is exactly the solution for the system? Why? Think about it. Now we are going to consider systems with possibly more than one solution or no solution. So the second example I would like to discuss today is first we are going to create the augmented matrix. And so we are going to capture all the coefficients and numbers here. So first equation, we have x, that means 1x, so you are going to put the number 1 there. And then 2 for y, 1 for z. And then the line is replacing the equal sign, and you have 1. Similarly, for the second equation, you have 2x, 4y. The z here means you have 1z, right? So you are going to have 1 and 3. And then you will have 4, 8, 3, and 6. Now we are going to use Gaussian elimination method. Right now, if you look at the first row, its first non-zero entry is 1. And so you want to zero out the number 2 and the number 4 below it. You want to make changes on row 2. In order to eliminate the number 2, you make row 2 minus 2 row 1. So that means row 1 stay unchanged. And so you will start doing 2 minus 2 times 1, that is 0. And then 4 minus 2 times 2, that is 0 as well. And then 1 minus 2 times 1, that is going to be -1. 3 minus 2 times 1, that is going to give you 1. Now, in order to make the number 4 here become 0, we have to make changes on row 3. So we will make row 3 change into row 3 minus 4 row 1. And so you are going to have 0, 0, -1, 2. So let's look at what we already had here. So we have the first non-zero entry on the first row, and all the entries below it are 0. So when you go down to the second row, the first non-zero entry is this one, and you will want all the entries below it to be 0. That means you will have to zero out the number -1 here.
So that means you will have to make changes on row 3 and make it become row 3 minus row 1. So that -1 minus -1 will make this one become 0. Alright, so next, row 3 will get changed, and that's become row 3 minus row 2. So 1, 2, 1, 1. The first row unchanged, the second row unchanged, the last row. Alright, so what we have already had is an echelon form. So you could have stopped here, or you can move further if you want. It's echelon form because this is the first non-zero entry, and then when you go below, this is the first non-zero entry, and then when you go to the third row, this is the first non-zero entry. So that's echelon form. As I said, you can stop when you have the first echelon form. You can either move further to make it a reduced echelon form, which will be better because you just look at the whatever you have at the end and tell, wait, this is the solution by looking at the right column. However, for this equation, if you pay attention, you know that you shouldn't move further. The reason is, if you look at the third equation, that third equation means the first 0 is on the first column, that is the x column. So this is 0x. Then this 0 is on the second column. That's where the y variable is. So that is like 0y. And this 0 is like 0z plus 0z. They all together will be what, right? All of these on the left will be 0. And we are looking for x, y, and z that will make 0 equals 1, which is impossible. So this implies that no x, y, z can do this. In other words, the system has no solution. Or you can say solution set is an empty set. All right, so now we are going to solve the following system. First, we are going to make the augmented matrix. We want to zero out the number 5 and the number 3 here. So we will use the number 2 to do that. But look, this number 2, if we use it to zero out the number 5 and number 3, that's possible. You only need to multiply 2 by a fraction, say 5 halves or 3 halves. But that will create a bunch of fractions afterward, right? So you wouldn't want to do that. So we are going to divide the first equation by 2 to make the number 1. So that is 1, -1, -1, 0. Keep the orders. And then we are going to use this number 1 to zero out 5 and 3, which will be easier. All right, so row 2 will change into row 2 minus 5 row 1. And then below you are going to have, all right, so now we are going to make changes on row 3. It will become row 3 minus row 2. This last equation means that if you rewrite it in the xyz form, it means 0x plus 0y plus 0z equals to 0, which is obvious, right? Because that means you are looking for xyz that will make 0 equals 0. It means that the third equation given to us was in fact a useless equation or a useless information, right? You just imagine each equation here represents some information that you collect from an experiment or from real life or from your project. Then you have the last equation, say 0 equals 0. That means a useless information, or in other words, it's in fact just the information that can be derived from the other two equations. And later on, you will see that such phenomenon is called linear dependence. All right, so what we already had is an echelon form, right? It will be echelon form. Instead of having 3 equations to look for 3 unknowns x, y, and z, now you only have 2 equations to look for 3 unknowns, which is not enough. Not enough, obviously, right? If you want to find a unique solution, that's not enough. However, this equation, if you rewrite it in the x, y, and z form, it's like, so the fact is that there are many pair y and z that can satisfy this equation. To name a few, for example, if you consider yz being the pair 0, 1/4, that's one option. You can consider 1/6 and 0, that's the other option, right? You can consider 6/10 and 4/10, that's another solution. There are infinitely many. Why do I say infinitely many? That is because you can start choosing z to be any random number. Say t, right? Then what's left is that you only need to choose y so that 6y plus 4t, because the z is the t now, equals to 1. And you can easily solve this equation and get that y equals to negative 4/6 times t plus 1/6. And so as you change the t choice, the choice of the number for z, you will modify the y so that 6 times y plus 4 times z, the choice that you made, equals to 1. All right, next we are going to focus on the last equation. We are using the backward method to find the solution. So the last equation means that you have x minus y minus z equals to 0, right? However, you have already found z, that is the random choice that you made, and y, that is depending on the random choice that you made. So you literally can rewrite the green equation as x minus y, which is minus negative 4/6t plus 1/6, and then minus z, that means minus the number that you made. And then you can solve for x. And so the solution for the system is something look like x, y, z equals to 2/6t plus 1/6 and negative 4/6t plus 1/6 and t for any real number t. So we have already had the solution, what the solution look like, all right? So if you are asked to write the solution set, then you actually just need to do this. The curly bracket stands for the set, right? And then you put the form that you had here. And then you say where t is a real number. So this is the solution set. This is a set. That is the set of all solutions. This solution, if you do some further examination on it, you actually can split it into the sum of 2 matrices. We are going to pull out the t as the scalar multiplication for the matrix of coefficients 2/6, -4/6, and 1. All right. Now in R3, this serves like a point that a line passing through. This will serve as the direction vector that shows the line's direction. Now, if you already learned Cal 3, then this is going to be the parametric equation of a line. So what it means is that if you have a coordinate x, y, and z, then the point is 1/6 for x, 1/6 for y. So this is x, y, and z. 1/6 for x and 1/6 for y. And 0 for z, which means that the point is on the xy plane. So this is the point 1/6, 1/6, 0. And then you have the direction vectors. How are we going to identify it? Right, we are going to identify what this is. All right, so that is 2/6 for x. So it's somewhere here. -4/6 for y. So it's pretty far here. And then 1 for z. All right, so first you identify the shade of the point on the xy plane. This is the shade or the shadow of the point on the xy plane. Now this is the shadow of the point where actually the point is. So it is 1 unit in the height. So you go up 1 unit. 1 unit height. So this is actually where the point is. All right. Now you have the point, then what is the vector? The vector that we have is in fact the following one. So this is the vector 2/6, -4/6, 1. So this vector serves as the direction for the line. And so you are looking for a line that is parallel to the vector here and passing through the blue point. All right, so this is the line that represents the solution set for the system. All right, so solving the linear system above, we actually get infinitely many solutions. That means you have infinitely many points on the line, of course, right? You already know that this is called the pivot entry. This is also called the pivot entry, right? Now, the column that contain the pivot entries are called the pivot columns. And the variables that corresponds to these pivot columns are called the pivot variable. And so x, y are called pivot variables. Okay, now let's look at this following column. This is called the non-pivot column. All right, and the variable corresponding to that is called the non-pivot variable. Now you have observed that for a system that has solution, the non-pivot variable can be chosen randomly. And because we can choose that randomly, we call it the free variable. Okay, so just some terminology. Note, pivot variables can also be free variable. Why? That is because if you look at this equation, it means you only need to choose so that 6y plus 4z equals 1. But in order to do so, you can first let z randomly be chosen and then choose y accordingly. However, you can do otherwise. We can choose y to be any random s number and then choose z accordingly, right? So that means the y itself can also be a free variable. Yeah, that's it, pretty much everything that I want to tell you. And there is an important theorem that I did not, and I won't prove this. We actually can prove this much nicer, much more elegant when we learn about linear dependence, independence, and equivalence. But there's a theorem say every augmented matrix is row equivalent to a unique row reduced echelon form. The nice thing is this is unique. So if you only have the echelon form, it may not be unique. But if you have row reduced echelon form, that is the unique row reduced echelon form for the augmented matrix. Right? So proof when it's time. Right? If we have time, we're going to go over that. That's going to be very elegant.